Okay, so the next one is exercise 6, and in this one we are given the field of rational numbers which we are denoting by f, and we are given a number of polynomials over f. For each one of them we need to calculate the degree of its splitting field over f. So let us recall briefly what we already know what splitting field means, but still, since we are going to calculate its degree. So for example, we consider this polynomial x to the power 4 plus 1. The splitting field for this polynomial is an extension E of f. The f is the field of rational numbers such that you can split or factorize this polynomial completely as a product of linear factors in the polynomial ring Ex, or equivalently you find all the 4 roots of this polynomial in E, and additionally this degree, the degree of E over f, should be minimal. It should be the smallest possible. Such a field E or such an extension E of f is called a splitting field for x to the power 4 plus 1. We have already proved theoretically that for any polynomial splitting field exists and it is essentially unique. Now we don't really need to find E itself, but rather we need to find this degree. So let's start the solution. Okay. Part A. Let's first see what we are writing here, and then I will explain. Let alpha be the complex number 1 plus I divided by square root of 2. Since the fourth power of alpha is minus 1, we have this factorization of our polynomial in terms of alpha. Okay. Why we are considering such a complex number out of nowhere in the beginning, that now it becomes clear after we have written down the complete factorization of our polynomial as a product of 4 linear factors. Okay, in each factor x appears as x and no higher powers of x are appearing. Now you can in fact verify that this is equal to this by a procedure which I think we discussed before also in another situation, in maybe the previous video or some video before that, I don't remember. But what you do, you just start multiplying the terms out, and whenever you encounter any power of alpha higher than the 4th power, you use this one. Or in fact, if you just encounter the 4th power of alpha, which you will if you, for example, multiply these two things first for some reason, then you just put minus 1 there. If you complete the procedure, you will see that you end up with x to the power 4 plus 1. So that way you have the full factorization. Hence, x to the power 4 plus 1 splits, that means it splits like this completely. Completely means as a product of linear factors. It can't go below that. These are the atoms of the universe in which this splitting is going on. Why? Because these are, being linear factors, they are irreducible polynomials or primes in some ring over which this factorization is happening. Hence this splits completely over, in fact now we are going to write over what? Over this field extension of F. So the ring that I was talking about just now is this ring, the polynomial ring over this field. Why? That's because you look at these individual linear factors and their coefficients. The coefficients of x, of course, 1. But what about the constant terms? Minus alpha, plus alpha, minus alpha cube, plus alpha cube. All of them are belonging to this field F alpha, which you obtain by attaching alpha to F, the field of rational numbers. So yes, in this universe you are having this factorization, and keep in mind, because F alpha is the field, Fx, this polynomial ring, is a Euclidean ring, and in that Euclidean ring this is a prime factorization, just like you have in the Euclidean ring of integers the prime factorization of 12, say. Okay. Now, because of this fact, we are now going to say something else. Okay. And that something else is this. It can be verified that no non-trivial factor of this polynomial in the polynomial ring Cx is in Fx. What is this? You compare x to the power 4 plus 1 with 12. This is the familiar Euclidean ring. Here we have its factorization as a product of its prime factors 2 and 3. Here we have the prime factorization of x to the power 4 plus 1 as a product of these 4 linear factors, which are primes in this universe. Okay. Now what we are saying, it can be verified that no non-trivial factor of this in Cx, in this slightly larger universe, in the universe of complex polynomials which contains this universe, is in fact in this still smaller universe. Why? That is because you see, okay, by the way, what are the non-trivial factors of 12? And by non-trivial I mean neither 1 nor 12, neglecting the minus things. Okay, 2, 3, 6, 4, such things, right? So they are the non-trivial factors of 12. Similarly, from this factorization and its uniqueness, because when you factorize an element in a Euclidean ring, not only do you get such a factorization, but it is essentially unique. What that means is that the prime factors that you see here, nothing else is going to come and give you another factorization. So any non-trivial factor of this one similarly will be formed from these 4 prime polynomials or from these 4 irreducible polynomials by taking maybe 2 of them or 3 of them, or in fact x minus alpha x plus alpha, each one of them is in fact a non-trivial factor of this. So what we are saying that none of such non-trivial factor, say another non-trivial factor is x square minus alpha square, which is this times this, and another one, yet another one is this times this times this. Okay, none of them is in fact in fx, that is none of them is a polynomial with rational coefficients. This one can verify. You have to consider quite a few multiplications or products, but you will see that none of them has all its coefficients rational numbers. That means what? That just simply means that this polynomial is irreducible over the field of rational numbers. Why? Because if that is not the case, then you can write this as fx times gx for some non-constant polynomials fx and gx, both coming from the polynomial ring fx. But then fx and gx are non-trivial factors, and we are saying that no such non-trivial factor actually belongs to fx. That is why now we are able to say that this is irreducible over the field of rational numbers. Another way of looking at this, and in fact you can write, instead of what we are writing here, you can just write like this: none of the 4 roots of this polynomial is in the field of rational numbers. That is why this is irreducible over the field of rational numbers, but we have chosen to write it like this, showing more directly the irreducibility of x to the power 4 plus 1 over f. Okay. So what are we going to write here next? Hence, this is irreducible over f, right? But you look at this equation, alpha to the power 4 is minus 1, which means that alpha is a root of this polynomial. In other words, alpha satisfies a polynomial of degree 4 over the field of rational numbers, and its irreducibility now proves that this polynomial is the minimal polynomial of alpha, and it is monic also. That's why we are saying the minimal polynomial, not a minimal polynomial. That's because if you combine minimality and monicness, you get uniqueness. Okay, so we are next going to write this irreducible over f, which implies this is the minimal polynomial of minimal polynomial of alpha over f. If you fix monicness, irreducibility implies minimality and minimality implies irreducibility. They become equivalent. So because this is the minimal polynomial of alpha, alpha now becomes what? Alpha becomes an algebraic number of degree 4. In other words, alpha is algebraic of degree 4 over the field of rational numbers F. Algebraic of degree 4 over F, and as a consequence the degree of the extension F alpha over F is equal to 4. We know, we have seen in the proof of that result, which links the algebraicity, I don't really know whether it's a legitimate word or not, the algebraicity of alpha over F and the degree of this extension over F. It's that linkage in which in the proof we have seen that the degree of this extension in fact turns out to be the degree of the minimal polynomial that alpha satisfies. That's why. Now, the splitting field of must contain both F and alpha. Why? The splitting field of course contains F by its definition, but it also contains alpha because it should contain all the roots of our polynomial, and alpha is one root of our polynomial. Hence, it also contains F alpha. Why? Because F alpha by definition is the smallest subfield of whatever extension we are considering of F in which all these things are going on. Say you can before everything else you already have this extension, right? The field of complex numbers. So F alpha is, for example, the smallest subfield of C containing both F and alpha, and the splitting field due to its nature must contain both F and alpha. So F alpha needs to belong to the splitting field or needs to be contained in the splitting field as a subset. But that gives us what? That makes the degree of F alpha over F less than or equal to the degree of the splitting field over F. But the splitting field by its very nature is the smallest field in terms of degree over which the polynomial splits completely. However, at the same time that is already happening over F alpha. That means F alpha itself is the splitting field. So we are just simply going to write next, hence the splitting field of this over F is F alpha itself. And we just stop here because you understand that our main aim has now been fulfilled. We have shown that it's the splitting field, and we needed to actually calculate its degree over F, which we have done. So that's it. So the required degree is 4. So this is our part A. Now in part B, because we have seen what we need to do, we are going to be somewhat sketchier. We won't write this many things. Now in part B, just like part A, we are going to start with a complex number which will turn out to be a root of the given polynomial, and in part B the polynomial is x to the power 6 plus 1. So let us start like this. Let beta be this complex number. Now the way I am writing these parts, the solutions to these parts, that raises a question about how to in fact find alpha, beta, these things. We are coming to that afterwards. Okay. Note that now it's a fact that beta to the power 4, all of these things can be verified, and in fact I urge you to verify actually that beta cube is I, and hence beta to the power 6 is I square, that means minus 1. From this we are going to get a factorization of x to the power 6 plus 1, similar to the one for x to the power 4 plus 1. So x to the power 6 plus 1 is equal to x minus, I can't possibly write it in one line, x plus I, because I need to write 6 factors. X minus beta, each one of them is linear and the given polynomial has degree 6, so 6 factors are needed by the degree formula, times x minus I beta square times x plus I beta square. And here also again, in verifying that this equals this, you start multiplying things out and then using these relations wherever they are needed. Ultimately you will get this. So x to the power 6 plus 1 splits completely over f beta, just like before, but there is a problem. I mean, it's not a problem, but you just see, when we say this thing f beta, or previously we had f alpha actually contained all the roots of x to the power 4 plus 1, that polynomial, and the roots were alpha minus alpha, alpha cube minus alpha cube. We could immediately see that all of those roots belong to f alpha. But now we can see from these roots I minus I, beta minus beta, I beta square minus I beta square, out of these 6 roots, readily we can see that beta and minus beta belong to this. But what about I minus I? What about these things? You need to actually see that they also belong to this. Otherwise, how are we saying that this splits completely over f beta? Luckily, we have this relation. I is in fact beta cube. So since beta already belongs to this field, which is an extension of f, so its cube also belongs to the field, because a field is closed under multiplication, so I should belong to this. Now because I and beta both belong to this, these roots also belong to f beta. So in brackets we write, note that I equal to beta cube belongs to f beta. Previously, in case of this polynomial, it turned out that this in fact is the what is that called, minimal polynomial for alpha, but here that is not the case. Why is that not the case? Because This is one polynomial over the field of rational numbers that beta is satisfying. Why? Because beta is a root. But there is a lower degree polynomial over the field of rational numbers that also beta satisfies, which comes from this equation. Okay. So its degree cannot be 6 because already we have found a lower one, 4. So from this equation we can now say that the degree of beta as an algebraic number is less than or equal to 4. Now beta satisfies the polynomial. From this we see that it satisfies the polynomial x to the power 4 minus x square plus 1, which of course is a polynomial over the field of rational numbers. Okay. Now if this polynomial is irreducible, then of course it is the minimal polynomial for beta, and hence by following all those arguments that we saw in part A, the degree of f beta over f would then be equal to 4, and yes, this is irreducible, and showing that it is irreducible is just like this one. You need to understand that we are considering this polynomial and not this polynomial itself because we have found a lower one. You can see one thing. This polynomial itself, I mean for this polynomial we are, you see one difference between this part B solution and part A solution. In part A solution, what we did, after we factorized x to the power 4 plus 1, we then went on to declare that no non-trivial factor of x to the power 4 plus 1 in Cx is in Fx. Here, however, that is not the case, and that is why this is not the minimal polynomial for beta. If you multiply these two out, what do you get? X square plus 1. So x square plus 1 is in fact a factor, a non-trivial factor of x to the power 6 plus 1, which is in Fx. So it is not irreducible over F. Or at least, I mean, what we are trying to say here is that we are not writing that thing here because that is not true, and in fact that need not be true because we are getting a lower degree polynomial to give us the degree of beta as an algebraic number. So we are going to write a similar thing like this for this polynomial, and so we continue like this, we don't stop here, and we have in fact the factorization of this thing in the polynomial ring Cx is this part, excluding this first two, and from this in fact you now can see why this is not irreducible over Q. Times x plus I beta square. In other words, x to the power 6 plus 1 is x square plus 1 times x to the power 4 minus x square plus 1. That is, x to the power 6 plus 1 has a factorization as a product of two lower degree polynomials, none of which is constant, but both of them are over the field of rational numbers. That's why this is reducible over Q, not irreducible. But for this one we can now write, it can be for this one it's true, but we are now going to write, it can be verified that no non-trivial factor of this in Cx is in Fx. So, unlike what we did there in solving part A, now our conclusion is direct and final. This degree is 4. Okay. In between we of course have those arguments, but we went through them once. We need not repeat that same thing again. What this means is that beta is algebraic over the field of rational numbers of degree 4. Since the splitting, this part let's just write it because after all we need to say that it's a splitting field. No? Since the splitting field of this contains f and beta, it is f beta. And just like before, its degree over f is 4. So although the original polynomials had different degrees, the first one of them was of degree 4 and this one is of degree 6, but the splitting fields for both of these polynomials over the field of rational numbers is 4. Then we come to part C. To split this one, we do not even need to give names to any complex numbers. Here the split is very easy. We have, because we are seeking, if we treat it as an equation by setting it equal to 0, then we are seeking the 4/4 roots of 2. Which you already know how to find. 2 of them are real and 2 of them are purely imaginary. X minus 4th root of 2, x plus 4th root of 2, x minus I times 4th root of 2, x plus I times 4th root of 2. So this splits completely over what? over we can say this extension of the field of rational numbers obtained by attaching two elements to it successively. In fact, it's a fact that if you are over a field of characteristic 0, like the field of rational numbers, the field of real numbers, complex numbers, all the familiar fields are of characteristic 0, then any such extension which you obtain by attaching a number of elements to the original field can also be obtained by attaching a single element. Okay, we will see these things. They are known as simple extensions. We will see this. They are coming. But we don't really need to know all those things. Here we can just simply see that the split is happening in a universe where we have both the fourth root of 2 as well as I along with all the rational numbers, and this is one such universe, the smallest such. Okay. Note that the splitting field of this must contain f fourth root of 2 and I, and as such is equal to this. Okay, why should it contain fourth root of 2? We understand why, because the fourth root of 2 is a root of this polynomial. So the splitting field should contain all the roots, and as such it contains this. But why I? That's because you see it contains fourth root of 2, but it should contain all the roots. Another root is I times fourth root of 2. Since it's a field, it should also contain their quotient. That means it should contain I, and because it contains all these three things, it should contain the smallest extension of f containing all this this number as well as this number. And due to its minimal nature, again same argument, the splitting, this itself should be the splitting field. Now we just need to calculate its degree. So here, instead of calculating the degree, first I argued and showed that the field itself is the splitting field. Now we need to calculate its degree. And in that direction, we first note this: since I is algebraic of degree since I is algebraic of degree 2 over this field, we have this degree equal to 2. We understand that if this is really the case, that I is algebraic of degree 2 over this field, then this is just 2 from our result. However, how are we getting that I is algebraic of degree 2 over this? We already know that I satisfies this polynomial over f, the field of rational numbers, and this is of course also a polynomial over this field, which is an extension of f. That means it's an element in this polynomial ring, and its degree is 2. Does I satisfy any linear polynomial over this field? Because I already satisfies this, and I mean what I am trying to say here is that if I satisfies a linear polynomial over this field, then I should also satisfy a linear monic polynomial over this field. But the only monic polynomial that I satisfies is x minus I, and this does not belong to this ring. Why? Because its coefficient minus I does not belong to this field. This field, whatever it is a subfield of the field of real numbers of the line. It cannot contain this non-real complex number minus I, and that's why in fact x square plus 1 is the minimal polynomial of I over this field, and that's why I is algebraic of degree 2 over this field, giving us this degree. Okay, now also by we already have something with us by exercise 2 of section 310. So you have to go back to the chapter on rings, 10th section of that chapter. There you see exercise 2. From that exercise we get this degree. In other words, the fourth root of 2, the positive fourth root of 2 is algebraic over the field of rational numbers of degree 4. Hence, the degree of our extension over f is equal to the product of these two degrees that means 8. So, and this is the splitting field. We already argued and concluded that. So here the degree of the splitting field over f is 8. Okay. Then that is part C. Then part D. For part D, the answer is a one-line answer. That's because it's a consequence of the next exercise. In this case, the degree is 4, 1 less than the degree of the exponent. And that next exercise, exercise 7, just says, it's this statement that the degree of the polynomial x to the power p minus 1 over the field of rational numbers is p minus 1, and where p is a prime. Here in place of p we have 5. Okay. So now we look at the final one. Okay, for the final one, I think now perhaps Let me just first write the roots of this polynomial down, then perhaps I should address how is it that we are getting these roots. Since the roots of are e to the power, I am writing two of them at once, okay, like this, 2 pi plus or minus 2 pi I divided by 9, then e to the power 4 pi I divided by 9, e to the power, I think 6 is also there. No, 6 is not there, but 8 is there. Ten pi I divided by 9 and e to the power 14 pi I divided by 9. In these are of course complex numbers. In C, our polynomial splits completely over this extension of I need ink. Just give me a moment. Over this extension of f. Let us first of all see if all the roots really belong to this or not. E to the power 2 pi I divided by 9, that of course is here because that's the thing we are attaching to f to get this extension. Its reciprocal e to the power minus 2 pi I divided by 9 is of course also there. This is the square of this element that is being attached. This is the fourth power, this is the fifth power, and this is the seventh power of that element. So all of them in fact belong to this. And since these roots are already in C, so this splits completely over this. Okay, now I said that I should address the question of how is it that we are calculating the roots. Now this is a difficult one to answer. In general, if a polynomial is given to us, it's quite difficult to know what the roots are. If the degree of the polynomial is very low, then of course you have methods. But if the degree is quite high, then the higher the degree is, the more the number of roots we have, and not just that, the more it becomes complicated to find the harder the task becomes. But still, none of these polynomials, I mean for this last one it looks like quite hard, but still if you just somehow play with polar forms of non-zero complex numbers, de Moivre's theorem, things that you have already seen in your study of complex numbers, somehow using these things you will eventually find one or two roots, and once you find say even one root, you can then do synthetic division to reduce the degree of the polynomial. That means you will then be able to find the other factor which contains the other roots, and then you go through a similar procedure. I, however, did not find these roots by hand. In fact, I cheated a little bit and I used an online. You can understand. I mean, it's not that we should just sit and do all the things on our own. That is impossible. You should seek help from wherever you can. In fact, not just seek, you should get help from wherever you can. Your final aim should be to find the solution. And that's just it. Okay. So now we have in fact found an extension of f that contains all the roots of this polynomial. The hard part is to, of course, find the roots, but once you have found them, it's just a routine matter to verify that all of them are roots. You just have to replace x with them individually and then see whether you are getting 0 or not. Okay. Now you can say, okay, fine. So we can write this as a product of linear factors that you will get from these roots, and then you will have to figure out whether this itself is the minimal polynomial of this number that we are attaching or not. Now keep in mind that in all these parts I am just simply directly writing that, okay, I know beforehand that this is the minimal polynomial. In this case, in fact, this is. And then I will just show that it's irreducible, that's all. But I have to actually know, and that takes time. For example, in part B, although beta satisfied this, but this itself is not minimal. We had to somehow figure out that beta also satisfies this lower degree rational polynomial. Now all these things have to be done. So behind all these solutions to each part, there is a lot of work. In spite of the fact that some of the work we have got from outside, but still you have to know all these things, whether this is irreducible or not. If not, then some factor which still these things satisfies, that is irreducible, because unless you find the irreducible polynomial being satisfied by this, you won't know the degree, and the degree is in fact the thing we are after. In this case it is irreducible. Okay. Now the question is, can we just simply write its factorization from these roots that you will get, and then say no non-trivial factor of this in Cx is in Fx and get the job done? You can do that, but we can do that. Simply saying this and actually doing it are two entirely different things. In the other parts, I said that one can verify that this thing can be done. I have actually verified. Okay. Now, as the number of roots increases and as the number of linear factors increases, that verification process becomes less and less feasible. You will soon be overwhelmed by how many factors you will have to verify, that none of them in fact belongs to Fx. So here we try a different method, and that different method is this. Now there exists a different method to show that this is irreducible over F, a natural homomorphism, showing that a polynomial is irreducible over some field in general is also very tough. Natural homomorphism psi from this ring to this ring arising from the homomorphism phi in example. I am going to explain what all these things are. 3, 3, 4, and in this regard, now we can wrap this up. In this regard, we can see something else. See the proof of lemma five, 3, 3. Suddenly, what are all these things? Let's see. Let me just first of all tell you about this function phi, which we have already seen in example 3, 3, 4. So this is the third section of the chapter on rings, and there we have this example. In this book, for some reason, the author denotes the ring of integers, or simply the set of integers, not by z or z, but by j. There may be some reason, I don't know why. And j2 is just the field with two elements, 0 and 1, which if you go back to the first preliminary chapter, there the author has defined it like this. These elements are not ordinary 0 and 1, but they are congruence classes modulo 2. This one consists of all the, this is the set of all the even integers, and this is the set of all the odd integers. Okay, so you recall those things. And what is phi? Phi is this homomorphism, which is defined like this. That means phi maps every integer onto these congruence classes, and the definition of n phi is this: it is equal to the 0 congruence class if n is even and the 1 congruence class if n is odd. It turns out, in fact, we have seen when we studied rings, that this is in fact a homomorphism, and this homomorphism naturally gives rise to a homomorphism between these two polynomial rings like this. Taking an element from here means what? You are going to look at a polynomial with integer coefficients where all the ai's are integers. Its psi image is this. You just replace each coefficient with its phi image. That's all. And this then becomes a polynomial here, and the fact that phi is a ring homomorphism gives the fact that psi is also ring homomorphism. Okay. So that's this whole thing. But now what? This is just pretty straightforward stuff. Now our aim is to show that our polynomial x to the power 6 plus x cube plus 1 is irreducible over the field of rational numbers. Say it is not. Suppose this is reducible over That means it can be expressed as a product of two non-constant rational polynomials. That's what it means to be reducible over F. Then by the corollary to Gauss' lemma, which is this theorem, again a result from ring theory, this is reducible over the ring of integers j. What does this corollary say? It says that if you have a polynomial which can be written as a product of two non-constant polynomials with rational coefficients, then it can also be written as a product of two non-constant polynomials with integer coefficients if your original polynomial has integer coefficients. In fact, that is the case here. Okay, so if it is, in other words, if it is reducible over F, then it's also reducible over J, the ring of integers. And what does that mean? That means something. It is this. So let me just write the polynomial like that here. Say you have now the fact that it's a product of fx and gx, where this is not a part of the solution. If you want, you can make it a part of the solution, but I have decided to suppress it. Where fx and gx are non-constant. That means each one of them has a positive degree. Either each one of them is either linear or quadratic or has some higher degree, but not constant. Polynomials in Jx. Then what is this? Note that the coefficients now are coming from our J2. So by the definition of psi, it's nothing but the psi image of the original integer polynomial. Because psi is the homomorphism, it gets applied on both the factors individually, and then we take their product because side respects multiplication. Okay, now what are we getting? Note that these polynomials, their psi, the psi images, the two psi images that we see here are in J2x or Z2x or Z2x. Is any one of them constant? Is that possible? Say fx, you see, we said that fx is non-constant. That means in general fx would look like this. Where n is greater than or equal to 1. in order for this polynomial, in order for the psi image to be constant, what would we need? We would need this. If we want fx psi to be constant in J2x, we need an phi, because you see, when you are going to apply psi on fx, you have to replace the coefficients with their phi images. All those phi images should be equal to zero. What type of zero? The zero element in J2. But that happens because you see, when this happens, then it will be the constant, this will be the constant polynomial a0 phi. Okay. But then an, all of these ai's that are appearing here should be even integers, right? But then an is even. Okay, if an is even, similarly, if this is constant, then this here also you should get even number. But you cannot multiply two even integers, because when you are multiplying fx and gx, how are you going to get the coefficient of x to the power 6? By multiplying the highest coefficients of fx and gx, because you have integer polynomials here. What is going to be the degree of 6? The degree, how are you going to get the degree 6? That you are going to get by multiplying the highest coefficient here, the highest term here with the highest term here. That is because the degree of this plus the degree of this should be equal to 6. But if you multiply two even integers, you are never going to get 1. Even integers are not units in the ring of integers. The ring of integers has only 2 units, 1 and minus 1. So that is why when you are multiplying two integers, if you have to get 1, either both of them should be 1 or both of them should be minus 1. So we are getting a contradiction here. Or instead of doing all these things or going like this, you can just simply use that fact also. If you express a monic integer polynomial as a product of two integer polynomials, then both of them should be monic. Both of them should be monic means what? If both of them are constants, then of course their product is just a constant again. But then how are you getting x to the power 6 plus x cubed plus 1? If one of them is constant but the other one is just simply a monic polynomial. But you have already seen that if it is, what I am trying to say here is this. I think I have lost the train of thought. Okay, we have so far obtained this, right? Similarly, the highest coefficient of gx would be even if we must have gx psi a constant in J to x. Thus, in either case, if this is constant or this is constant, we won't get this. Thus, both both must be non-constant. Even if one of them is constant, then you run into a problem. But as you can see, I was in fact struggling to make sense of this part. So you need to make it more clear. Okay, if you also find it somewhat confusing that we are actually getting a contradiction here, if these things happen, you need to make it clearer. I am, however, just simply writing thus both this and this because I thought of it previously, but I think there is some gap in my thinking. I don't believe that whatever I have done is wrong in some way, but somehow I have been unable to satisfactorily explain. That's what I am saying. Thus both this and this are non-constant. That is, this is reducible over J2. So reducibility of our original polynomial over f, that supposition led us to the reducibility of our polynomial, original polynomial over J by the corollary to Gauss lemma. But then that gives rise to reducibility of this polynomial over J2, but its reducibility implies that this polynomial has a root in J2. So the infinite possibilities that you have in J, the ring of integers, has now been reduced to only two possibilities, 0 and 1. If you put the 0 congruence class in place of x here, you are getting 1. So 0 is not a root of this. If you put 1 here, then you get 1 plus 1, that vanishes. It becomes 0. Again you get 1. So neither 0 nor 1, and that means nothing in J2 is a root of this. So how can it be reducible? This is false. So x to the power 6 plus x cube plus 1 is irreducible over f. Hence, the degree of our extension over f is 6. So in this case the degree is 6. Now you may raise a question that Lucifer, you said that instead of writing, or in fact actually verifying that no non-trivial factor of that factorization or our polynomial in Cx is in Fx, verification of that takes a lot of time, but it seems like this method is also long. No, this method is not long. Once you go through all the arguments once, you will see that actually it is quite easy, it's feasible, and it actually reduces your work, your effort. Okay, so there the solution ends. We can in fact solve another one, but let's just stop it here itself. That's because I think I'm a little tired today. That's why I became somewhat clumsy here. But I again urge you to make this part absolutely clear, and if you are unable to understand or even find a small gap in my argument, please immediately let me know in the comments. We will try to rectify things. So with that I end this tonight, and tomorrow let us once again solve our group theory problems from Lie. Then next week we will go back to Galilean group and ring problems. So with that I sign off for tonight. So see you tomorrow with Lie problems. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.